quite a few people on, about 40 participants. So we will get started. Good morning, everyone. This is Lakshman Rao. I'm the president of IIT Alumni Association of Southern California. Want to welcome you all to this exciting session we have planned for you today. We have two fantastic speakers for you who are going to talk about the space theme. That's something really close to my heart, like near and dear. I went to IIT Kharagpur myself, did my bachelor's in aerospace and got my master's as well. Currently, I'm a project manager at Boeing. So really, space team and airspace is very close to me, and looking forward to this really excellent talk today. So, and we have our moderator, Gunjan Bagla, who's going to be leading this event. So thank you, Gunjan, for offering to do that. Before I get into the event, I want to spend a few minutes talk about the organization. IIT SoCal is a 501c3 organization. We basically represent more than 2,000 IIT alumni in the Southern California region. And we are also affiliated to the Pan IIT USA organization. So our goal is to bring together the IIT alumni community and showcase, the great contributions that IITians are doing, and also create a forum to network, engage, share ideas, and help each other to become a more vibrant community. So, this has been a challenging year. Last year, we did an in-person conference, which was really successful. We've had picnics in person, but this year, because of COVID, we having to do these events online. So we've done a few before, and this is a really big one where we are having a lot of people turn up to hear from our panelists and, just learn about this, the technology and the fantastic work they're doing. So really fortunate and grateful that we can bring this to you. I would like to start off by thanking our sponsors. Let me share my screen here. So because we are a 501c3 organization, this would not have been possible without the support of our sponsors. So I'd like to acknowledge TCS, who's our 2-year platinum sponsor that is really supporting us. And then we have Ravi Tilak from Almex, who's our diamond sponsor. And then we have Praful Kulkarni from GKK Works and Canon Design, Guld Havan from Applied Membranes, and then Amrit Ventures are among our sponsors. In addition, we also have support from the Consulate General of India, San Francisco, and Fly Homes, Tushar Garg. Some additional sponsors are Raghu Sugavanam Family Foundation and an anonymous 1970 IIT Kanpur graduate. So thank you again to our sponsors for supporting us. This would really not have been possible without them. So with that, I'd like to introduce our moderator for the event, Gunjan Bagla. Gunjan is one of our prominent IIT alums in the Southern California area. He's been the past president. He's been the president of Pan IIT USA. He's really known as the India expert for his, views and perspectives on how to foster India-US relationships. So really thankful for Gunjan to be hosting this event and moderating this event. A few ground rules. This event is basically Q&A, which will be moderated by Gunjan. We do want questions from the audience. So please use the Q&A feature, and you can put your questions in there, and we will ask the panelists. So thank you again. Gunjan, I'll hand it over to you. Please take it away.
Well, thank you, Lakshman, and thanks everybody for organizing the event. Thanks for attending from all the various places that you have dialed in. I know Saturday is morning, so early is not probably the best time, but we have a good reason for that because one of our panelists is dialed in all the way from New Delhi, India. And so we wanted to make a time that is convenient or at least reasonable for her. Uh, so before we get started, I'd like to run a quick poll, Sushant. If you can ask the audience the questions. Yeah. Okay. Are you from Southern California, somewhere else in the US? Are you joining from India or other parts of Asia? We just want to get a sense of who's online. Okay, so as the numbers are coming in, I assume these results are being shared with the audience as well. And I do see that there's a fair number of people who are not IITians. So while you're still answering the poll, or has it stabilized now? I guess it has, right? So we have a third of the participants from our local chapter in Southern California, and then a fair number from Asia, and also a fair number from the rest of the country. And I won't get into the IIT representations. You can see them for yourself. There's a competition among the IITs, a friendly competition, but we won't address that right now. But a fair number of people are not IITians. So let me first start by talking about the IITs very briefly. Some of you who are non-IITians might already know that the CEO of IBM was recently appointed and is Arvind Krishna, and a graduate of IIT Kanpur. A few years earlier, the CEO of Google and now the CEO of Alphabet is an IIT Kharagpur graduate, Sundar Pichai. Sundar was a winner of the Pan IIT Alumnus Award some years ago. And there are many, many other IITians who are very prominent in their fields. You know, my son went to Stanford. He graduated from Stanford, which is the most competitive school in the US. They take 4% of applicants. The IITs take 0.92% of all applicants into their undergraduate program. So you can imagine it's a very, very intensely competitive program. And IIT alumni are present in across many, many sectors in the United States. I won't dwell on that further right now. Um, let's also talk a little bit about Southern California, since many of you are joining from outside the area. The business around space and aviation is really, for the last 100 years, has been centered in Southern California. So we'll talk about Bob's accomplishments very soon here, but going back many years, uh, Southern California was the place where Howard Hughes designed the Spruce Goose, the largest wooden aircraft ever built, and he piloted it and flew it, I think, for about 90 seconds. It was built during the war, the Second World War, and it flew in 1947. Some years later, Northrop Grumman designed the Flying Wing, the so-called B-2 stealth bomber. And a lot of that work was done right here in Southern California. The space shuttle was largely built here in Southern California in Downey by Rockwell. Okay. The first space missions were conceived of by the RAND Corporation in Santa Monica. And of course, the Jet Propulsion Labs, which is part of Caltech, has been responsible for virtually every major development in extra Earth or away from Earth kind of exploration. So going to the moon with the first unmanned satellite, going to Mars, going to Venus, going to Jupiter and Saturn and beyond the solar system. All of those projects have been led by the 5,000 engineers and scientists working at the Jet Propulsion Lab. And so the work we'll talk about is really a continuation of that effort. Um, the let's start, however, with an introduction of one of our young alumni, Dr. Nancy Agarwal. Nancy recently completed her PhD at MIT, And her work was so distinctive that she was given a special award for her work by a national or global organization. She is now a postdoctoral fellow at Northwestern University, and you can read the rest of her bio online in the announcements. I won't dwell further on it. Her work is on gravitational waves. And we are so glad, Nancy, that you're joining us from New Delhi today. Tell us briefly about the picture we see behind you.
Yeah, hi everyone. And first of all, I would just like to thank Gunjan for the introduction, and thanks the organization for inviting me. I'm really happy to be here, and I will be happy to answer all of your questions today. Yeah, so the picture behind me, maybe I'll move out of the way for a second here, is the experiment that I built for my PhD that Gunjan was talking about. It is what we call a room temperature optomechanical squeezer, and we can get into more details of that later on.
Okay, great. So Nancy, you work on gravitational waves, and tell us very briefly, for people who don't know what gravitational waves are, what are they and how big are they?
Sure. So maybe I'll just share my screen to show some visual aid as I explain. Uh, so gravitational waves are basically ripples in space-time. So when Einstein sat down and wrote his theory of general relativity, these sort of just fell out of that theory or are just a byproduct of that theory. So they basically just the space-time itself stretches and squeezes as these waves pass through the space-time, and even us, like even we are getting stretched and squeezed every time a wave passes through us. They're emitted by all systems that are moving and have a non-spherical shape. The more mass there is, the more faster the system accelerates. The more non-spherical or non-symmetric it is, the bigger the gravitational wave will be. Typically, these gravitational waves are measured in this quantity that we call h, which is a strain. So we can think of that as a change in length, which is delta L divided by length. So the question that you can ask is, I have this 1 meter room or object. How big or small is that object getting as a gravitational wave passes through? And the answer is typically on Earth, you can expect that strain to be 10 to the minus 21. So every meter is getting changed by 10 to the minus 21 meters. These gravitational waves are, as I said, emitted by these very non-symmetric objects that are moving fast, that are heavy. So I have an example of that kind of a system for you guys. So one canonical system that emits these gravitational waves is a pair of black holes that are orbiting each other. So when these black holes are orbiting each other, they're going to emit gravitational waves. And so the gravitational waves are taking the energy out from this system, which makes them actually get closer and spin faster, which makes the waves even bigger in amplitude. And that goes on until they merge and make one single black hole, give out a very final blast of gravitational waves, and then it's remote silence forever. So
Okay,
I think
so
that's...
tell us, Nancy, why this is important. 10 to the power of
Sure.
minus 21 is not something that I feel when it goes through me, and most instruments can't measure it. So why should we care?
Yeah, so I think, actually this is maybe the best way to answer why should we care, is that we should think about gravitational waves as a way to obtain completely new information about the universe around us. So the easiest analogy I can give you is, imagine if you could see me, but you couldn't hear me. You would only be getting half of the information that I was trying to convey or that I was relaying out. So that's what gravitational waves are. Before gravitational waves, we were only seeing the universe through electromagnetic waves or light. But now we are seeing the universe through this entirely new type of information carrier, which is gravitational waves. So just like electromagnetic waves, they come in all different frequencies. And depending on what source created these gravitational waves, we get to learn a lot of new information from from those gravitational waves.
Got it. Got it. Okay. Hey, I invite the audience to send in questions at any time. Okay. You don't have to wait until the end of the talk. This is a conversation rather than a lecture. So audience members, if you have any questions for Nancy, please send them. So we already have a question for you, and this is about what kind of instruments do you use to measure this strain? And I think that's part of the work that you did in your PhD, right?
Yes,
How do you
absolutely.
detect, how do you
I was an
measure them?
instrumentalist. Yeah. So how do we measure them? So again, I will start with just for people who just joined in, how big these waves are. I said that the strain that they exert is about 10 to the minus 21. So just to put that in perspective, because it's basically 1 followed by 20 zeros after the decimal point. What does that even mean? That's a very tiny number. So put it in perspective, I have converted for you how much would the size of the Earth change if a gravitational wave passed by. So the size of the Earth would change by about 6 proton radii. So yes, the question is, how do you go about measuring something like this small? There's two parts to that answer. First is, since you have to measure a small L, but technology only exists to measure big changes in length, the only option is to actually make the length as long as possible. So that's what we do. We go to the government and we ask them for a big piece of land, whatever the biggest land that we can acquire or get to do our experiment. And the answer to that political question happened to be 4 kilometers at the time, which was tens of years ago, 3 decades or something ago. We were given 4 kilometers of land. So now what that means is that if I put L equals 4 kilometer, that means I have to measure something that is 10 to the minus 18 meters, which now is 1,000 times smaller than the radius of the proton. So that's what you get. You get 4 kilometers, you have to make do with it. So how do you measure 10 to the minus 18 meters with something that's 4 kilometers? So the next part of the answer is you use lasers. So the way we do this is we take a really quiet laser and we send the laser one in the north direction and one in the east direction over here. So that kind of looks something like this, and then we reflect it off from 2 mirrors. And the interferometer is set up such a way that both the sine waves are perfectly canceling out. So there is no light when there is no gravitational wave. But when a gravitational wave comes by, it shrinks one arm and stretches the other arm. So that changes the time it takes the light to go in both of these arms. And that messes up this perfect cancellation condition that we had. And that lets some light out on our detector. So then we know, okay, we've got a gravitational wave.
Awesome. Awesome. Wonderful. Thank you so much, Nancy, for that explanation. So does the expansion of the universe cause a distortion in these waves, and how do you factor for that when you make these measurements?
So the expansion of the universe it has been predicted. I'm going to stop this animation so that it doesn't distract us. The expansion of the universe has been predicted to be associated to produce some gravitational waves. Those gravitational waves are at very low frequencies, and those are not detected by LIGO. So LIGO has some frequency reach, which maybe is seen over here in this view graph, where LIGO is here and the audible frequency range in the kilohertz frequency range. But the expansion, the gravitational waves that come from expansion would be very low frequency range, actually somewhere even over here. So those would not affect LIGO's measurements of gravitational waves. We do have experiments, and by we, I don't mean me, I mean scientists have experiments to measure those very low gravitational waves that tell us about the expansion.
Terrific, terrific. Let me see if the audience has any other questions. I think there's a few very technical questions which I'm avoiding because I want the answers to make sense to the rest of the audience as well. So tell us what you're working on at Northwestern right now, Nancy.
Sure. So one thing that I am actually, this view graph itself is useful for that, is what you see here on the right. Actually, as of a year ago, this spectrum was ending right about here. So what we are trying to do at Northwestern is adding another gravitational wave detector that's like a miniature gravitational wave detector over at the high frequency side. So this, I would say, is like one of the things that I am building out at Northwestern. Let's see. So that detector looks something like, where is it? Here we go. So this is what it looks like. It's also a Michelson interferometer, but it's very small as compared to the few kilometers that LIGO is. This is going to be like 1 to 100 meters long interferometer, and hence the guitar in my photograph there. The other project that I'm a part of in Northwestern is also a dark matter project where what we are trying to do is look for this new source of dark matter, which is called an axion. This experiment looks for a new interaction that shouldn't exist in our current understanding of physics, or what we call the standard model. This interaction shouldn't exist. And we have to build a very precise experiment to actually measure this interaction. It requires us to build this very big contraption, or I like to call it a Frankenstein of a cryostat. It's taken us a year, more than a year, to actually even just design it. It's going to take us another year to build this cryostat to 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 hunt for this new dark matter candidate.
Awesome. Well, thank you so much, Nancy. Thanks for sharing all of that with us. I hope you can stay on for the rest of the call. I know it's late in India, and maybe we'll have some questions for both of you towards the end of this call. So let me now
Awesome.
switch to Dr. Bob Balaram, who is the chief engineer of the Mars Ingenuity project at the Jet Propulsion Lab here in Pasadena, California. Um, some of the people have joined in a few minutes late, so I just want to perhaps reference some of the things that I said early on. Jet Propulsion Labs is run by Caltech, and Caltech has a strong connection to the Indian Institutes of Technology, as it was one of the two leads, in addition to MIT, that set up the Indian Institute of Technology at Kanpur under the Kanpur Indo-American program. There's a fairly significant number of IIT alumni working at JPL, which we'll talk about perhaps if we have time later on. JPL is responsible not for any jets or any jet propulsion. The name is perhaps a little misleading, and Bob, correct me if I'm wrong on any of this, but the JPL works largely on things that happen outside the orbit of the Earth. So Mars, Venus, Jupiter, and beyond, all the way outside the solar system. What the Voyager aircraft, for example, have left the solar system, and they were designed and conceived of and in part built at JPL. So Bob Balaram is a graduate of IIT Madras in South India, and has his PhD and other degrees from RPI in New Jersey. He has been at the Jet Propulsion Labs for at least a couple of decades, working on what they call entry, descent, and landing systems and other important initiatives. So those of you who have followed space and the Martian projects in recent years will have heard about the Sky Crane, and Bob was probably involved in those, but that's not what we'll be talking about today. Today we'll be talking about something that is a landmark really in the development of aviation, as important, and perhaps some would say more important than the first flight of the plane by the Wright brothers in Kitty Hawk. This is a device that's lighter than a bald eagle, and it will fly on the planet Mars sometime after February, once the Perseverance rover sets foot on the red planet. Bob and his team have been working on this for a number of years, and it's a pretty incredible project. We could probably spend all day talking about it. but we'll focus on just a few things. So Bob, first of all, tell us, what will this Ingenuity, this helicopter, do on Mars? You know,
Thank you,
what is
Gunjan.
its mission? What will it accomplish?
Thank you, Gunjan. And by the way, it's 35 years at JPL. You make me feel much younger by saying it's only 20. Makes me want to go back and write the JEE all over again. Yes, so this helicopter is what we call as a technology demonstrator. It's really designed to validate and prove that we can achieve this kind of aerial mobility capability on Mars. So in that sense, there is really no scientific role for this helicopter. It's really all an engineering demonstration. It's very similar to the little Sojourner rover that some of you may recall from the late 1990s, this little thing about 10 kilograms that went to Mars as part of the Pathfinder mission. And then since then, subsequently led to the development of the Spirit and Opportunity rovers, the Curiosity rover, and now the Perseverance rover that we are hitching a ride on. So what is going to happen is they will find a spot on Mars after a month or two after they land in February 18th, after they finish their own commissioning. They will drop us off in a small little airfield that they will find, which has some nice, flat characteristics for our test flights. And we will spend what's called sols, 30 Martian sols. Sol is a Martian day. It's about 24.5 hours. And we will be conducting up to about 5 flights. There's about a 3-day cadence between flights related to, getting the data back, analyzing it, and then sending up the next flight. Each flight is progressively going to be more complex. The very first flight is just going to be a repeat of what we have tested here on Earth. Go up, hover, and come back down. But once we get that under our belt, if that's successful, we will, start excursing sideways and then coming back and landing. And all of that engineering data will inform the design of future Mars helicopters, which will have more of a science role. And we are beginning to look at even some designs for that right now. They'll probably be at maximum, maybe about 20 kilograms, carrying, 2, 3, 4 kilograms of science payloads. And that's possibly the future where we can provide this new way of exploring Mars to future missions. But this one is just purely a technology demonstration, and it's got a very limited scope. It's just 1 month out of the entire Perseverance mission timeline, where they're really off looking for astrobiology type of samples that they're collecting for eventual return.
So in future, can you visualize a situation where humans might fly on a helicopter, on a future helicopter?
No, I don't think so. Not on Mars. Mars is with 1% of the Earth's atmosphere density. It's equivalent to flying at 100,000 feet here on Earth. Now, what does help us on Mars is the fact that the gravity is only about 40%, so that helps. But nevertheless, the rotor blade diameters get extremely unwieldy and large. So I personally don't see anything much more than about 20 kilograms. So it's not quite your science fiction of Edgar Rice Burroughs or whoever dreamt of flying on Mars. Mars is a difficult place to fly. It's the most challenging place to fly on the solar system. The easiest being Titan, which there's a mission reaching there in the 2030s that will likely fly in Titan. But Mars is pretty tough to fly. So 20 kilograms is the upper limit, is what I would think it would be. Maybe 30.
Got it. Okay. So there are a series of challenges that you had to plan for. And it's not just a matter that where at Kitty Hawk, they built a bicycle attached to a glider and some controls for the wings and an engine, and they had everything to go to do their very short flight. Here you have to think about getting your aircraft all the way to Mars. And so tell us a little bit about the challenges of taking a 4-pound device and sending it up into space and the kind of stress that it has to go through.
Yeah, so let me talk a little bit, just even from the design of the helicopter itself. It has to be extremely low mass because you have that thin air, which translates into rotor diameter and very high power required. So normally in an engineering system, there's usually mass that you can throw at the problem. You can say, well, if something is a little too weak, let's make it thicker. Let's clearly partition out, two distinct subsystems and let them build their own thing and not try to look for efficiencies across building it. So the main challenge was just to build a very lightweight, I would almost use the phrase gossamer, but it's not quite that fragile, aircraft. But then it has to be a spacecraft. And when I say it has to be a spacecraft, it has to survive launch loads, launch vibration loads. Just to throw out a number there, the vibration loads that we designed to are equivalent to about 80 Gs. That by far is the largest driving mechanical forcing thing on the system compared to anything that it actually will see when flying on Mars. It has to survive the vacuum of space. It has to survive. All the components have to have a reasonable chance of working in radiation environments. So there's a certain screening process involved. We are flying a lot of commercial off-the-shelf parts in order to get the performance, in computing and battery technology. All of those need to be, space-worthy. And there, during the descent onto Mars, there is the entry, descent, landing, which are sustained, peak G loads, 7, 8, 9, 10 G types of loads. There's a parachute snatch load. So all of that has to be factored into an aircraft, and you don't have the luxury of just making things more rigid and more heavier and trying to get to a solution. So that was sort of one dimension of challenge. The other dimension of challenge is we are on a major flagship mission for NASA. So we have to be absolutely safe to this big mission. We can't jeopardize it in any shape, way, or form. And we have to interact with a vast organization that builds these, billion-dollar plus types of spacecraft. And we're a small, very agile little technology demonstrator trying to fit in with this, major flagship project. And that presents its own technical and organizational challenges. Technically, for example, this is an astrobiology mission looking for samples. So we have to be extraordinarily clean. We had planetary protection engineers, auditing us and sampling us and swabbing us, making sure we weren't carrying, too many spores of, various organisms to Mars. We have to be extraordinarily clean because we don't want to go into vacuum of space and outgas, stuff that will then go deposit in the cold vacuum of space onto a sensitive science instrument. So there are all sorts of challenges that are just related to, being on such a major flagship mission as a passenger. And that has, translates into all the engineering constraints. And then the third dimension, which I'll just mention, is it has to be designed for testing. And what is that test program? There is no textbook out there which says this is the way you test a Mars helicopter. So there is a whole design of what in the engineering world we call V&V, verification and validation, which is really the test program. So how do you navigate through the test program in the most optimal way? What are the holes in that test coverage? How do you manage that risk? So there are multiple dimensions. And by the way, not that flying on Mars was easy either. There are special airfoils, special wings. There was some unique control challenges that Mars threw at us that we don't find here in helicopters on Earth. So it's been quite a wild ride, but a very satisfying journey.
Okay, great. So were there other IIT alumni involved in supporting the Ingenuity program?
Yes, somewhat indirectly, like our high fidelity simulation toolkit that we use for looking at all the vehicle dynamics was built by an IIT Kanpur, I believe a friend of yours, Abhinandan Jain. So Abhi's team developed the toolkit that we used for our modeling and simulation stuff. And there were other IITs who were IITians who helped more in a support role in the sense that they were in the management chain. Like there's Gani Ganapati, who's a thermal section. So we did thermal. Mars gets very cold at night, minus 90 C. So all these things have to survive overnight in Mars. So there's a lot of thermal modeling and unique thermal design attributes to this vehicle. And so Gani Ganapati's section, people in his section were very directly involved. So both a combination of, technical support as well as managerial support that help make this happen.
Yeah. So, Bob, you'll be interested to know that every Thanksgiving, my family and I spend the day with Abhinandan Jain and his family, and Gani Ganapati and a number of other JPL people are usually there. The discussions are quite stimulating. My whole family really looks forward to the conversations we have with the JPL engineers and scientists whom we meet there. It's always a treat. And for those of you who are in Southern California, you should know that once a year, JPL actually holds an incredible open house. I think it's usually in May, and they didn't do it this year, I guess, because of COVID. But they actually open up the labs, and you can walk in and ask questions of the people who are working on these amazing projects. So if you Google open house on the JPL website, you can find more information about that. So Bob, tell us a little bit about this thermal management. You know, you're building an aircraft. Well, actually, no, even before we go there, you know, most aircraft on Earth run on some version of gasoline, and now there's some electric and solar powered aircraft. So what is Ingenuity? Have you packed a few hundred gallons of aviation fuel to take with you?
No, we are what you on Earth you would call us a very green vehicle, but this being Mars, I guess you should say we are a very red vehicle. We are fully solar powered. We have on top of the rotors a solar panel with very high efficiency solar cells, quadruple junction metamorphic cells, which are very high efficiency tuned for the Mars spectrum. We harvest the energy during the course of an entire day on Mars. And we store that energy in 6 lithium-ion battery cells. And then when we get to flying, the energy is discharged from those cells through custom direct drive motors that were built specifically for this vehicle. And we achieve about anywhere from 90 seconds to 2 minutes of flight based upon that solar cell energy that we have accumulated. Actually, most of the energy we accumulate, a good 2/3 of it, it really just goes to run heaters that keep our batteries from freezing in the night. And they go to run what we call as heat to operate heaters, which warm up certain critical components up to an operating temperature. So when we do takeoff, it's a balmy, you know, only a -40 or -30 degrees centigrade, and not the -60, 90 we had at night. So in that sense, we are, completely self-contained. Once we are dropped off by the mother rover, we don't come anywhere close to it. During cruise, which is where we are right now, we top up the battery to a safe cruise level every 2 weeks. We sort of trickle charge the battery. In fact, we just did our 5th battery charge just yesterday. So everything's looking good as far as the battery goes in cruise. But once we're on the surface and separated from the rover, we are on our own and we're harvesting our own energy through our own solar panel.
Awesome. And so what is the day that you expect? This Perseverance will land on February 18th. And you said it'll take about a month before.
My expectation is they'll take a month to 2 months for them to commission enough of the rover to sort of like begin a drive to look for our place. So once they start that, let's say a month and a half or so, then about at the 2-month mark, I think we would have found a location, and then they'll spend about a week deploying us onto the surface, and then they'll drive off to a safe observation distance about 100 meters away. And then we will commence our 30-day clock starts at that point. So I would anticipate the April-May timeframe is when it's going to be a lot of fun on Mars.
Okay, great. And for the audience, please continue sending your questions for Bob. I see some interesting ones popping up already, and we will address those shortly. And Bob, I'm continuing to ask naive questions. I've done a lot of reading about your work, but I want to present the questions in a naive way. So once Ingenuity is ready to fly, so all of us are imagining you sitting with 2 joysticks in front of you and making Ingenuity go forward and backwards and roundabout. And I don't think that that's really going to happen, right?
No, we have a significant time delay, between for radio waves to get to Mars and come back. And then there are a number of relay hops also. So we will be getting telemetry back only, once a day or twice a day, depending on the orbiter passes. So both from a fundamental physics limitation, speed of light. So that's the one bit of intersection I have with Nancy's talk. But so that's a fundamental constraint for any vehicle that we send to Mars, that you cannot joystick it because the response times are not, possible. And also more fundamentally, like with the rover, even if you just send up a command sequence, which is what we do with the helicopter also, which basically says just go from, this XYZ to another one, to another one, and we send up the string of those, what we call as waypoints, and the helicopter will execute. But in a rover, you have the luxury that if something bad happens engineering-wise, you can stop and ask help from home. We'll be in the mid-flight, and so we have to have a sort of a safing feature where we land right away in case we run into a problem. So we have to be able to do autonomous takeoff, autonomous landing, and then autonomous waypoint following in the sky. That's kind of has to be built into any vehicle that goes to Mars.
Okay, excellent. So let's talk a little bit about the aerodynamics of this rotorcraft. From the pictures, I saw that you have two rotors. So one is turning clockwise, the other is turning counterclockwise, so that the aircraft is stable. You don't have a little tail rotor as most Earth-based helicopters do. What were the special challenges in building this for Mars? In designing and building this, did you use the same computational fluid dynamics and the kinds of things that our host Lakshman Rao would be doing with the Boeing commercial aircraft, or were there some special challenges that only exist on Mars?
Right, so there was a lot of CFD analysis, both fluent 2D codes as well as other 3D Navier codes that we use in the design, and a lot of testing that came into play. But what's unique about the aerodynamics, other than the obvious fact that you got to spin rotors very fast, you got to keep the tip speeds subsonic. You really don't want to enter, sort of the transonic, supersonic range aerodynamics. But the low density of the air puts you into what's known as a low Reynolds number flow regime, where a Reynolds number basically tells you the balance between inertial and viscous forces in a vehicle, and and controls whether you get laminar flow or whether you get a turbulent flow across the cross section. So there are airfoil shapes that had to be tailored to the low Reynolds number regime in order to generate the right amount of lift and not stall out. And then the other issue which we ran into was a bit of a surprise for us is any helicopter blade tends to flap up and down. It's just the nature of being mounted as a long skinny thing on a hub, right? On Earth, it turns out that that flapping motion is damped out by the thickness of the air surrounding it. So the control system doesn't feel it as much, and it can continue with this job of stabilizing this essentially unstable platform, but control systems are designed to do that. But this flap mode really messed things up, because on Mars, you don't get that aerodynamic damping. And that was one of our first test programs where we said, oops, I guess there's more to aerodynamics here than just generating lift. I mean, we had done all the wind cross-section, this, that, everything we knew could generate the lift. But then control proved to be a challenge. And the way we avoided that problem in the vehicle that's on its way is we made the blade incredibly stiff at the price of some mass in order to push those flapping frequencies away from where the control system would be bothered by it. But that was quite a surprise. We had a big test failure where we had a scale vehicle that we were trying to experiment with. And at that time we were saying, let's have our experienced pilot joystick it, in a big chamber at 1 atmosphere. Everything looks good. Let's, as an existence proof of control, make sure he can control it. When we pumped the chamber down to Mars densities, we pumped it down and he couldn't fly it. It was going all over the place, jumping around. And that's when we realized that there's more to aerodynamics than just lift, but also there's some control challenges. But we solved it, we moved past it, yeah.
Okay, so I think you've answered the question that was asked by, just a moment here. I want to make sure that I acknowledge the audience members here. Oh, it seems to have disappeared. I think somebody from IIT Kharagpur had asked about the aerodynamics, and I hope Bob's answer covers it. If not, you can send a follow-on question.
Yeah, we have a number of publications out there too. So there are AIAA papers which talk about some of the details of all of these things too.
Awesome, awesome. Okay. Now there's a question from Professor Suketu Bhavsar, who actually spoke at our event last year. And he is at Cal Poly Pomona. And he says, hey, did you say a vibrational load of 80 Gs? Did I hear that correctly? And
Correct.
Is that the kind of vibration humans face in manned spaceflight? I suspect the answer is no, but go ahead and fill us in, Bob.
See, the spacecraft, there are a number of mechanical systems, that come into play. But typically for any kind of unmanned system, that is a reasonable, and it's a function of the size. There's different objects of different size will respond differently. But there is a distinction we are making here between the static G-force that you feel just from acceleration, that's your F equals ma, versus the vibration, which is really an acoustic phenomena. You have these huge sound waves from the firing of the engines that are getting into the canopy that's enclosing the system. They're reflecting off everything and amplifying. And yes, that vibration spectrum, if you look at the sort of the RMS value, of what that root mean squared value of what that vibration spectrum looks like, it's about 80 Gs. I'm sure in the manned program, they, control that a little bit through whatever special seeding out, and all those kinds of design things that they put in. But in terms of just the sheer mechanical strength of what parts need to be designed to, a good rule of thumb is for something of about the 2 kilogram size, 80 Gs is a good number. And that's what we have, all our parts are designed to, at least that. In addition to, having passed various qualification test programs on real vibration tables, which are mimicking what the spacecraft would see. So there's backed up by tests, but 80 G is a good starting number.
Got it. Okay. Now there are a lot of questions about basic statistics about the program that are coming through. And I would encourage
by the way, just as a small point on the vibration, 80 Gs may sound scary, but if you drop your phone on the floor, that's seeing about 1,000 Gs, It's IIT guys, I have to say this technically, it's your stroke length, how far you drop it by how far of a deceleration distance, take the ratio of the two distances, you get your G. So if you drop from a meter and it stops within, a millimeter, you get 1,000 Gs. Yeah. So that's what your phones are designed to. So it shouldn't surprise you that it's quite a comfortable place to be, even though it sounds like a big number.
Right, right. Thanks so much for that, Bob. So there are many questions coming about basic statistics, how big is the aircraft and, how far can it fly? And I'm not going to take time for those questions right now, because if you go to the JPL website, you can find those basic answers. I'm going to try and concentrate on things that we can only learn from Bob that may not be listed on the JPL website in an obvious manner. So one question that has come up is about the dust storms on Mars that we hear about. Okay.
Yes. So first of all, if you saw the movie The Martian, it was a very good movie and technically very good in almost every axis and technically correct. But for the purposes of dramatic tension, they had a Martian dust storm do, all kinds of incredible damage. Because the density is 100 times less, correspondingly, the effect of any wind on Mars is much less. A 100-mile-per-hour wind on Mars is equivalent to a 10-mile-per-hour breeze here on Earth in terms of the dynamic pressure you'll feel. So it really does not do damage in the sense of, being affecting, ripping things apart and stuff like the movie The Martian. But it does have effect in two ways. One is, what dust storms do is they churn up the dust that's in the surface, everything, and raise it into the atmosphere. And so what happens is you get a sky that begins to look a lot like our Southern California skies over the last 2 weeks, where there's a lot of particulate matter in the air. And so your solar power that you can either get through the panels or even harvest, to stay warm from your thermal surfaces drops. So that's the major effect of dust, that you can have this atmosphere opacity characterized by something called tau, an extinction factor, that can hurt you on the power side. You can also get accumulation on a solar panel over time, which will eventually degrade the solar panel performance. You can get dust that can go into a lot of these mechanical moving parts. We have a dust seal approach that tries to mitigate all of that. And so those are the real consequences of dust. Not so much that it's a Martian storm will generate winds that will drop you, but a Martian dust storm could make the atmosphere quite opaque. Now it turns out that we are fortunate that this tech demo is landing in what's a low dust storm season on Mars. And we're only going to be operating for 30 days. So for our purposes, the dust doesn't really affect us from an energy perspective either. And we are designed to handle pretty aggressive winds and things during flight. We'll also pick our first flight during the early part of the day where the convection has not yet built up and set off all these eddies in the atmosphere that might make it more windy. So before we try, flying later in the afternoon, our first flights will probably be mid-morning to sort of account for the fact that we want to be in the low wind condition. So all of that is tied into atmosphere and dust, but dust storms as such is not something we're worried about.
Got it. Okay. You referred to some kind of a test chamber earlier, Bob. And can you describe, how big is this test chamber, and are you able to reduce the
Yes, let me talk about that.
Yeah.
Yes, so at JPL, we have a space simulator chamber, which is 25 feet in diameter. I'll speak feet because that's the way it got designed, and about 80 feet high. By the way, it's not the largest chamber at JPL. The largest chamber in JPL is in Ohio, at a place called Plumbrook, which is just huge. But this is pretty big, and all of JPL spacecraft go in there. And typically what you do is you pump down to 10 power minus 5 torr. You test your spacecraft systems. You can control the temperature in this chamber to a very high temperature, or you can flood the walls with liquid nitrogen and get very low temperatures. We have 30 arc lamps in the basement, which through a mirror system come and focus light onto the center of the chamber. So we can simulate everything from solar conditions at Venus distances as well as Mars distances. So in this chamber, what we did typically for our test program is we had a little 1.8 kilogram test article, sometimes on a fixed stand, sometimes on a gimbal, and later on, in free flight conditions. And we would pump the chamber down to vacuum, backfill with carbon dioxide to exactly the right pressure that we needed. And we did a lot of our testing at Earth ambient temperatures, room temperatures, but we also did a few tests at colder temperatures to make sure there was nothing funny happening that was beyond our model predictions as to what happens when the CO2 gas turns cold. So all of that is a big facility, but the one interesting side effect of that is it's not a test setup where you can say, oops, I forgot something. Let me run into the chamber and adjust thing, or I left a piece of something there. The chamber also has to be kept extremely clean. So that's why you see people even in bunny suits, even when they're working in the chamber. And if you want to, it takes about an hour and a half to 2 hours to pump down and an hour and a half to backfill. So it's not a quick, you better have your checklists and things and done just right. Otherwise, this chamber, and as you can imagine, especially if you go cold, this chamber is not cheap to operate either, because it just requires a lot of boiling of liquid nitrogen to keep it cold and so forth. So ambient tests are a bit more relaxed, but if you're running a full-scale test with low temperatures and solar illumination, it's quite an enterprise.
So at what point do you feel confident in a project like this, where there are so many unknowns, so many things being done for the first time? When do you say, Bob, okay, I'm ready to go to Mars?
Well, I think we are at that point, but it's, if you start my timer of when this started, when I briefed the JPL lab director, Dr. Charles Elachi, 7 years ago, and he gave the green light to start looking at this. I just jokingly say it, but it's not incorrect to say there's been some kind of crisis every week, usually at a technical crisis. But that's one of the things I think we IITians, at least I can speak for the IIT Madras people, we got exposed to every form of engineering. So I know exactly what I know in every engineering discipline, and I know exactly what I don't know in every engineering discipline. So when I have a team together, I know exactly where the sort of skeletons are, what to ask, what to do, but there's been a crisis in one shape, way, or form. Like our spore count on our something is coming in too high. What do we change in terms of cleaning? The aerodynamics is not quite working out. The lithium-ion battery safety, there are some questions. We had a test failure. Mass of the system is getting too high. How do we cut it down? Etc. The flight software has, some issues. So it's been a wonderful. So I don't mind those kinds of crises because we think as engineers and we can go about solving them with engineering and physics behind us. So that has been, we've done everything we can in terms of a test program. We've flown in the chamber. We have done environmental testing where we subject the helicopter to vibrations and cold and pyrotechnic shocks. There are a lot of, I don't know if people realize, but in a spacecraft, there are lots of small explosions going off all over the place. Like on Earth, if you want to separate two pieces, you take your screwdriver and you start undoing something and things come apart. No, in spacecraft, you blow an explosive charge, and the number of techniques in which separates things, okay? So when that explosion happens, there's a pyrotechnic shock wave that ripples through the entire structure, and you have to be able to withstand that. We had some interesting failures in that we had to overcome and so forth. So we've been through every possible testing that we can do on Mars. We have gone through all the review process to feel comfortable about it. But it still could be a glitch. We are a tech demonstration. We are not built to extraordinarily high quality standards that a flagship mission would do with a lot of QA and a lot of redundancy in the system. So there's still a glitch or two that could mess us up somewhere between now and those first few flights. But I'm optimistic that we'll have a success on Mars.
Bob, can you tell us what was the most difficult or challenging part? I know you had a crisis every week for the last 7 years, but is there one thing that stands out in terms of a challenge where you said, oh, this could jeopardize the project?
Well, I think when we had that first failure where the pilot attempted to control this thing under Mars conditions and just couldn't achieve control.
Yeah.
That said, this is completely unknown and we got to get to the bottom of it. But less than a year later, we built a full-scale version of the system that flew by itself autonomously without even needing the assistance of a gravity assist. We use a gravity assist tether for the final vehicle because at 1.8 kilograms, we can't fly that particular vehicle in Earth's gravity. But we flew an 850-gram vehicle, which had the exact same rotors, but we buried all the power supply and computing, below the floor. So this thing flew up, but it was trailing below a umbilical that, was giving it power and, all the commands for it to actuate all the systems. So that failure where we had that, that it couldn't fly this thing, was new and shocking in some sense because it was unexpected. Got all our helicopter experts at NASA very excited because to them this was a brand new, problem. They've been working on Earth helicopters forever, and now they got a chance to chew on this. So that got them excited. So that was probably the biggest crisis moment technically. But we had control structure interactions where we went unstable when we first spun up a motor because the torsional board on one of the structures coupled into the sensor feedback. And so the vehicle thought it was, it misreacted to the torsional vibration, thinking there was a rotation in place. So that's a classic control structure interaction where we almost, fell apart because of the vibration shaking on one of our test vehicles. So a number of things like that. There are a fastener that came loose, because somebody forgot to use Loctite on the particular test vehicle build up. So at high speed, we had a fastener let loose. So yeah, there were, you name it, we had it.
Got it. Okay. So a couple of last things here. First of all, are we in a position to show a photograph of the helicopter, Sushant? Can you bring up the images?
Yeah, well, I'm not going to project, but I've sent you the deck, so please use that.
Yeah, right.
The second slide should be the one.
Yeah. If you can bring that up when you have a chance, Sushant. And in the meantime, let me ask you a little bit of a different question. JPL has been working with the Indian Space Research Organization on a number of initiatives from time to time. And there's a big one going on now called NISAR, which I think is the most expensive Earth sensing satellite planned to be launched. Can you tell us a few words about what is happening with NISAR and the collaboration with the Indian Space Research Organization?
I don't know too many specific technical details. It's a synthetic aperture radar, which is where the SAR comes in. And the N and the I think stands for NASA ISRO synthetic aperture radar. So it's NISAR or NISAR, I'm not sure exactly how they pronounce it, is an Earth observing system that will use active radar, synthetic aperture radar, to learn all sorts of things about, not only the topography of the Earth below, but by looking at all the various characteristics of the signal, they can tell you everything from, soil moisture and vegetation and this and that and everything. So it'll be a very important Earth observing platform, especially in this day and age where climate change, regardless of what you think may be causing it, definitely there is a fair amount of activity in that area and has consequences for everybody on the planet. So I think having that kind of platform with two of the sort of premier space agencies, in my view, coming together to address it is a great thing. So I'm looking forward to seeing all the stuff that NISAR can do for us.
Excellent, excellent. Is this the main picture you wanted to show, Bob, or is there?
That picture, I think, is actually the screen, which has, go to slide number 2.
Sorry, I don't have that one.
Well, I sent a deck to you, Gunjal, which had about 10 slides. But so if that's
yeah.
But,
if you don't have that up, that's all right. That's all right, Sushant. Much of the imagery is actually present, including some video simulation on the JPL website, and we can send links to some of those out.
I can try to bring it up. Let me see. I'm not a Zoom. We use something else where I am. But if someone can tell me how to share a screen, I can try. But I'll do that in the background. Let me see if I can do that. But let's see. No, I'm not sure I can know how to share things in Zoom. Share screen. There we go. Let's share screen too. Let's go slideshow. So can you guys see that?
No, not yet.
Okay. No, you're not seeing any of this? Oh, well.
Okay, that's all right. That's all right. I think people can find it on the website, and we will send those links out. Lakshman and Sushant, is there anything else we need to cover?
I think we have some audience questions.
Okay, do we have time for those still? Yeah, there's lots of audience questions, and I've tried to address some of them, but let me see.
Can you guys see this now?
Yes.
Okay, so let me just take 30 seconds. That's a solar panel. That's our antenna that we have a base station on the rover that it serves as a communication path. Those are the counter-rotating blades. I will give brownie points to any IIT person who can explain what those are. That's a swash plate. Those are our motors, 23 pole pair motors. That's a fuselage, which is mostly has all the electronics, has all the battery, has a CO2 gas cap, a very high absorptivity surface. Those are landing legs, latchings, dampers, feet. And then that's why we want to go to Mars, because it can, same reason people like to fly drones here on Earth. What all could it do? That's someone going to that. That's where we are on the belly of the rover configuration. And that's what it looks like right there before they put on a debris shield cover, but that's where we are under the rover. And that's kind of like, what our flight plans look like on Mars. And that's some of the team that was taking delivery of the helicopter as part of, fixing it onto the helicopter as they were going to put it onto the rover. So those are the people in the JPL clean room.
Are you in that picture, Bob?
No, I'm not allowed to touch this thing. So I have not touched this helicopter myself. I don't have the training and nor the time to take the training to be certified safe to actually touch. So yes, I have not touched the helicopter myself.
Okay, so Sushant and Lakshman, we are at our 1 hour. If we have time for more questions, if Bob is willing,
yeah, I can stay. I can stay. It's up to you guys.
Okay.
Yeah, let's continue, Gunjan. Yeah, I think if Bob is available, yeah, let's keep going.
Okay, all right. Let's go into the questions that we haven't addressed yet.
I'll keep it on, okay, just in case some questions come up and I need to refer to a slide to answer it better. Yeah.
So what is the level of quality of components used in Sigmas and how is it assured?
Like, we don't, I don't believe in all of that stuff. My approach to this has been very, very individual and specific. So we have a mix of commercial off-the-shelf parts and, obviously custom fabricated things. So this is not a mass manufactured system where I think your statistical significance of, how much of stuff on your product line, meets your certain quality standards, and which is where, no, we just pay tremendous attention to all the process engineering and the materials engineering that goes into it, all the test programs preceding adoption of a part, all the prototyping that essentially tells you that it's going to work, and it's a lot of testing after the fact to the extent that a technology demonstration program can do it to convince ourselves that it works. So there is no statistical X sigma anywhere in terms of the process. This is a one of a kind. I'm not even quite sure how you would do all of those things.
Got it. Well, we have a student from IIT Kharagpur who wants to answer your bonus point question. Her name is Shilpa Sajeev, and she says that what you pointed out were the contra-rotating propellers to cancel out the torque.
Well, almost right. So these are what they call as Chinese weights. So the tip of these things, if you can see on my mouse, there's actually a heavy weight there. And that provides a restoring moment to counteract something called the tennis racket effect. So what that means is any body that has got a slightly off, asymmetric inertia as it rotates, it wants to sort of flatten out in the process. And this provides a countering moment, which means that the servo system that is actually trying to change the pitch angle of these things at the equilibrium, flight conditions, trim conditions, it doesn't have to do much work. These guys are providing enough of a countering torque so that at a hover pitch, it's doing very little work. And so the servos, there are 3 servo motors here and 3 servo motors there. They do the least amount of work. So if you meant that, you got an A+.
All right. Thank you very much.
In the helicopter literature, they're called Chinese weights. I'm not quite sure why, but they're called Chinese weights.
Chinese weights, okay. Now some P. Aragade, I'm not sure what the full name is. Their question is the work that you're doing be applicable to designing a flying car on Earth?
In fact, there are 2 levels of answers. So we had very active participation from some key folks from the aeronautical side of NASA. NASA, in addition to doing space, there's a whole aeronautical research mission directorate, which is very active in looking at electric cars, not only from the technology itself, but in terms of everything from air traffic management and so forth and so forth. So some of the same people who helped, design these things up at NASA Ames for us are very active in that side of the house. And so I think there's been some useful cross-fertilization in terms of design tools and design approaches and test approaches and things. There's some, but it's a loose coupling. I think it's more in the spirit of people on the same team, benefiting from this. but not anything explicitly. I think there is the whole lithium-ion batteries or other battery technology with high specific energy and high specific power. Once that gets a certain threshold, I think you'll see, and the air traffic management side of it is handled, you'll see ubiquitous electric aerial vehicles, I think.
Got it. We must have an attorney in the audience because there's a question about, do you patent all the work so that private companies can take advantage of what is happening at JPL?
No, not specifically on these things. There is a whole NASA intellectual property office that, so we do internally file what we call as new technology reports as appropriate, and Caltech and NASA, can choose to patent what is done, but there is nothing specifically here that has gotten into a patent from, at least from the JPL side, that I'm aware of.
Got it. Okay. There's a question I think that might have been for Nancy. Let me just bring it up as well. Nancy is still on the call, relating to the work that it might be happening in India concerning the LIGO project. Nancy, do you want to address that?
Sure. I am not the right person to ask. I am not really involved in the LIGO India project, but I can say that it's going on. We have a site that has been decided. It is in Maharashtra, and there's a lot of institutions here that are leading that effort for building LIGO India. It is running on schedule, albeit a few delays because of the virus. Yeah, it's getting a lot of its parts from the second LIGO detector that was being built in Hanford, Washington. So those parts are getting shipped, and they're currently in the stage of training scientists. They ship off scientists to the US. They go to LIGO, they get trained, and they come back, and they will hopefully build it at some point.
Okay. Bob, there's one or two more questions that I didn't get to, and I think one of them might have been from our chapter president. What are the third-party suppliers that have been involved in a significant way in the work on Ingenuity? I think I read that Lockheed has done something, and maybe AeroVironment. But
yeah. So specific to the helicopter itself, the rotor system that you're seeing out here, which is basically from here up to that, the blades, the composites, the motor, the servos, that was all built by a company here in Southern California called AeroVironment in Simi Valley. AeroVironment is famous in the past for, McCready, interesting person if you ever go read up about him. He's the founder. The first human-powered flight of an aircraft, the first human flight across the English Channel. The chief engineer from the AeroVironment team that was responsible for the rotor system, a guy called Matt Keenan, built a flying hummingbird, which has all the hummingbird flap dynamics and very miniaturized. So they're known for being, building very small drone type systems, very lightweight, very compact, and they have a sort of their whole very good R&D sort of way of translating that into reality. So from McCready's heritage. So AeroVironment built this. The solar panel, the solar cells are by a company called Solaro. So those are sort of the two of the big sort of, by and large, the AeroVironment is the main thing, and Solaro on the solar panel. Now, to get us off the rover, there is a deployment system, which is basically takes you from this configuration and then basically lets us be on the ground. That particular deployment system was built by Lockheed Martin at Denver, and it's called the Mars Helicopter Deployment System. So it's a very key system because it has to work. It has to blow off this cover. It has to, rotate the system sideways. It has to then, release all the launch locks and the leg locks, a lot of pyrotechnic and something called frangible activity to get that done. So Lockheed Martin built the deployment system. So those are some of the major third party, if you will. Plus we had COTS parts. This is flying a Snapdragon processor from Qualcomm. There's a bunch of automotive processors which are redundantly doing a lot of the flight control. There are commercial, Garmin laser altimeters. There are MEMS IMUs here, which are again commercial. So the bunch of commercial parts, but the big subsystem assemblies are the ones I mentioned.
So these commercial off-the-shelf components that you have used, one of the questions that had come up is how do you deal with radiation on Mars? So these things weren't designed for kind of cosmic radiation.
Right, and luckily Mars is, relatively benign in radiation, much more than Earth, but it's not as bad as being in Jupiter or someplace where you have the heavy ions trapped in those Jovian orbits. So we effectively did a screening kind of program where we looked at both total dosage. We looked at the inherent, process technologies and, gates and how are they built and substrates and so forth. And we also characterized it from what's known as single event things, which are, basically what happens is either a galactic cosmic ray or something hits the chip and, deposits charge. And depending upon how bad it is and what the underlying process technology is, you either get a bit flip or you can have a permanent damage to the part because of excess current draw. So we looked at a lot of parts that we were looking at and basically did effectively a screening against total dosage and single event matchup. And then we built in redundancy, and for critical components, we made sure that they were radiation hard components as opposed to commercial off-the-shelf components. So there's sort of a hierarchy of redundancy and screening and testing that leads us to believe that for our 30-day mission, we're in good shape.
Okay, excellent. Well, Bob, thank you so much for taking this time and giving us a real wonderful engineering overview of one of the most remarkable initiatives that has happened at JPL and probably anywhere in the world. And good luck to you. We'll be watching to see what happens in April and May. And we hope you'll come back and give us an update maybe a year from now as to what your next adventure at JPL is going to be once this is done. So thank you very much. And thanks, Nancy. I'm going to hand it over to Lakshman to close it out.
Yeah, I also wanted to just say thank you for inviting me. And, I was telling my wife the other day, I think I intellectually peaked the day I took my JEE, and it's been downhill ever since. So it's been a fun journey, but, I think we all feel that sometimes that we probably all hit our peak right about that time.
Yeah.
So anyway, it's been a fun thing to work on. And thank you so much for giving me the opportunity to share it with you guys.
Right.
Well, thank you very much, Dr. Balram, and thank you very much, Dr. Nancy Agarwal and Gunjan Bagla. This was a really fantastic event. I mean, I thoroughly enjoyed every minute of it. As Bob just mentioned, IIT just takes you on this really amazing journey. And, there is just like world of possibilities to what you can do. So really, really great to see, like the amazing work that Bob has done and, what we can aspire to. There's, gravitational waves and what we're doing with the all the testing, that's really going to transform and enhance our understanding of the universe. So I think there's really a lot to come from that. So Nancy, we are really excited to hear more about that. And Dr. Balram, I mean, really can relate closely to all the technical aspects of doing a complex project and working with cross-functional teams and working on really these challenging problems for something that's never been done before. So wish you all the best, all the success, and we'll be hoping to hear from you on how things go. So thank you very much again. I would like to acknowledge once again our sponsors for supporting us. Couldn't have happened without them. Thank you again, Dr. Balram and Dr. Agarwal for being with us and sharing your knowledge and experience. Gunjan, thank you very much for moderating this event. Really a great job, and you are really excellent at sharing IIT perspectives and kind of really melding the story together. So thank you very much. My volunteer team, Sushant Agarwal and Roop Goyal, did a fantastic job of putting this together. So thank you guys. You're amazing. And of course, the IIT volunteer team. So thank you very much for this. And lastly, all the participants. We had almost 100 attendees today. So that is really great turnout. So thank you very much for attending here. I know many of you are from India, so it's pretty late. So thank you for joining us. And we really had a great show today. We would like to do a quick survey to collect some feedback. So Sushant, if you can bring that up, that'll be, this will be the good time to do that.
It will come up once everyone gets disconnected. They will see this survey.
Okay, that's good. So it'll be when we sign out. So before I close out, I just want to share with you that we have another event coming up. So IIT SoCal is going to partner with Pan IIT USA, and we're going to have a talk on digital transformation of corporations. So that will be a national event. So we are planning for October 10th. And one of our IIT SoCal alumni is going to be the panelists, and Gunjan will be the moderator for that event. So please stand by for that. That's going to be another great event. And yeah, so that's what I want to share with you. So again, thank you all for joining us. If you have any feedback for us or any comments, please reach out to us on email, alum@iitsocal.org. And you can also visit our website, iitsocal.org, to learn more about us. With that, thank you again. I wish you all to be safe and take care of yourselves. And thank you very much. Take care, everybody.